Hello everyone, today let me introduce RepVGG, a model proposed at CVPR 2021. CNN architectures have evolved from LUNet to AlexNet and then to VGG. But simply stacking more layers doesn't always improve accuracy, due to problems like vanishing gradients. To overcome this, ResNet introduced multi-branch structures with residual connections enabling deeper, more trainable networks. However, during inference, these complex structures increase latency and memory usage. In deep learning, while training can take time, inference is expected to be fast, so this becomes a critical disadvantage. To address this, RepVGG was introduced. The most distinctive feature of RepVGG is that it uses different network structures during training and inference. During training, it adopts a multi-branch architecture consisting of 3x3 convolutions, 1x1 convolutions, and identity branches to enhance the model's representational power. However, during inference, this complex structure is reparameterized into a single 3x3 convolution layer, turning into a simple, plain model. This process is called structural reparameterization. In other words, the model is trained with complex structure to achieve high performance and then transformed into a simple structure for fast inference. So, RepVGG is a model that achieves high accuracy during training and high efficiency during inference. When the input and output have the same number of channels, height, and width, a RepVGG block contains a 3x3 convolution, 1x1 convolution, and an identity branch, each followed by batch norm during training. And their outputs are merged using element-wise addition. This process can be expressed mathematically as follows. Given an input tensor M1, the M2 is computed by applying each branch followed by batch norm and then summing the results. The detailed formulas and notations can be found in the appendix at the end of the slide. After training, these are merged into a single 3x3 convolution layer. An important point to note is that during inference, the batch norm parameters are fixed. That is, mu, sigma, gamma, and beta are constants after training. Because of this, we can convert batch norm into a single linear transformation. This equation shows that how transformation works. The original convolution kernel W is modified by multiplying it with gamma of sigma, resulting in a new kernel W prime. The bias is also adjusted using formula minus mu times gamma over sigma plus beta. As a result, a convolution to batch norm sequence can be fused into a single operation of the form M consolved with W prime plus B prime. That simplifies the computation during inference. Now, let's apply the previously explained transformation to each branch of the block. First, the 3x3 convolution branch already has the desired form, so it can be used without modification. Next, for the 1x1 convolution branch, we use zero padding to embed the kernel at the center of the 3x3 matrix, effectively expanding its size. Finally, the identity branch is expressed as 1x1 convolution with an identity kernel, which is then expanded in the same way into a 3x3 kernel. Once all three branches are converted into the same 3x3 kernel format, we transform the batch norm layers in each branch into their equivalent linear operations as explained earlier. In the final step, we sum the resulting 3x3 kernels from all branches and also add their corresponding bias vectors together. As a result, the entire block can now be represented as a single 3x3 convolution operation with bias, significantly simplifying the model during inference. This diagram visualizes the transformation process from two perspectives, structure and parameter based. In this paper, the authors conducted experiments on RepVGG using the following setup. First, RepVGG comes in multiple versions, varying in depth and width. As shown in the table on the right, the models are categorized into the RepVGG A and RepVGG B series based on their layer configurations. Each model also differs in the width expanding ratios denoted by the parameter A and B. For example, RepVGG A0 is a lightweight model, while RepVGG B3 has the most complex structure and is expected to deliver the highest performance. The hyperparameter settings shown here are based on RepVGG A0 model. Here are the experimental results of RepVGG models trained on ImageNet. In this context, speed refers to the number of images processed per second, essentially the inference speed. In table on the right, you can see the comparison between the RepVGG models and other well-known CNN architectures like ResNet in terms of accuracy, flops, and inference speed. Among them, the largest model, RepVGG B2, reached 78.78% top 1 accuracy compared to ResNet 152, but with 1.5 times faster inference speed. These results show that despite its simple structure, RepVGG delivers highly competitive performance, both in accuracy and inference speed, compared to the high precision CNNs. Based on these results, we actually re-implemented RepVGG A0 and compared it with ResNet 1.8. We initially tried to train on ImageNet, but due to slow training caused by I/O bottleneck, we switched to Cypher 100, which has lower resolution and fewer classes. The image size was reduced from 224 to 32 pixels, and the number of classes from 1200. Both models were trained for 200 epochs using aggressive augmentation, auto-augment, mix-up, and cut mix since the dataset was significantly smaller. We used identical settings for both models to ensure a fair comparison. Since the original RepVGG code was designed primarily for ImageNet, we had to make a few modifications to adapt it for Cypher 100. First, Cypher 100 images are very small with a resolution of 32 by 32. In the original RepVGG implementation, the stride in the early layers, particularly stage 0, was set to 2, which caused a feature map to shrink too rapidly. To address this, we modified the file by changing the stride of stage 0 from 2 to 1, making it more suitable for smaller input sizes. For the ResNet model, we also made some adjustments to better fit Cypher 100. First, we modified the initial convolution layer, conv1. The default setting downsamples the input too aggressively, which is not ideal for small images like those in Cypher 100. So, we changed the kernel size to 3 by 3, set the stride to 1, and using padding of 1. We also removed the max pooling layer following conv1. This layer normally downsamples the feature map again, but for small inputs, it discards too much spatial information too early. Therefore, we replace it with identity to better preserve spatial details in the early layers. Now, let's look at the experimental results comparing RepVGG A0 and ResNet 1.8. Regarding accuracy, ResNet 1.8 achieved a top 1 accuracy that was 4.77% higher than RepVGG A0. This is slightly better than the numbers reported in the original paper, likely because we used the well-optimized torch vision model's implementation of ResNet 1.8. In terms of inference speed, RepVGG A0 processed approximately 22,215 images per second, while ResNet 1.8 processed about 21,969 images per second, making RepVGG A0 roughly 1.1% faster. In short, RepVGG offers efficiency, while ResNet 1.8 achieves better accuracy. This reflects a clear trade-off between speed and accuracy, making model choice dependent on your priority. Thank you for your attention, and I'll be happy to answer any questions you may have.